Hello, madam. We are Team 19 presenting assignment 2 for CST 108 programming practice. Our topic today covers two data structures implemented in C, a doubly linked list and a stack built using a singly linked list. I am Ayub Hisham Hussein and I'll be presenting task 1, the doubly linked list. My teammate Akhtar Suraya will follow with the second task, the stack. Before we dive in, here's a quick roadmap. For task 1, I'll walk you through the node structure we used, then the 5 core functions is empty, insert node, find node, display list, and delete node. How we'll handle edge cases like an empty list or invalid values, and finish with a walkthrough of our sample output. After that, Suraya will take over for the second question. Okay, let's start with task 1, the doubly linked list. So every node in our doubly linked list stores three fields: data, which holds the actual value, prev, a pointer to the previous node, and next, a pointer to the next node. Having links in both directions means we can walk the list forward or backward, and once we have located a node, we can rewire its neighbors in constant time. On top of that, we wrapped everything in a second type def called doubly linked list, which just holds a head pointer. This means every function only needs to take one doubly linked list, a list parameter, instead of passing around a raw node pointer. And by design, our insert node always inserts at the front. So the new node simply becomes a list head, which keeps our head bookkeeping simple. Let's go to the next slide. First is empty. It's a simple check. It returns 1 or true when list to next head is null and 0 otherwise. This function is called first inside find node, delete node, and display list. So we never accidentally dereference a null pointer. Next, insert node. Since it takes a pointer to the list struct, it can update list to head directly. No need for a pointer to pointer. Here's what happens step by step. So we allocate a new node set. Its prev to null and it's next to the old head. Then we link the old head prev back to point at this new node. And finally, we reassign list to head to this new node. As you can see in the diagram, after inserting 20, it becomes the new head, and 10 now correctly points back to it. Okay, on to the next slide. Now for find node, we walk the list from list to head using a current pointer along with a position counter that starts at 1. If current to data that matches the value we are looking for, we report its position and return. If current reaches null instead, that means the value isn't in the list. In our example here, we're searching for 15. So the counter shows position 2 and we get a match. Then let's talk about display list. So it prints the list in a way that visually shows the doubly linked structure, starting with null, pointing back, walking left to right, printing each value separated by the going forward, and closing with pointing forward null. Worth noting, because it's a doubly linked list, we could just as easily traverse it backwards from the tail, which is actually useful for double checking that our previous links are correct while debugging. Okay, let's talk about delete node. So it first searches for the target value using a current pointer, exactly like find node. There are 3 possible outcomes. So case 1, the value isn't found. So current reaches null, so we print a not found message and just display the list unchanged. Case B, we are deleting the head node. That's when current to prev is null. We update list to head to current to next, and then set the new head's prev back to null, so it's properly terminated. Case C, we're deleting a middle or tail node. Here we set the current to prev to next to current to next, and if a next node exists, we also update its prev to point back correctly. Only after all these pointers are rewired do we call free into bracket current that order matters. Otherwise, we lose the references we need. So we made sure to handle 3 edge cases carefully. First, an empty list. Is empty guards find node, delete node, and display list before they ever touch list to head. So instead of crashing, we print a clear list is empty message. Second, a single node list, when that one remaining node gets deleted, both its prev and next are null. So it naturally falls into case B. Delete head and list to head becomes null, printing list is now empty. Third, an invalid or missing value. Both find node and delete node loop until current becomes null. If there's no match and delete node, then reports not found and simply redisplays the list unchanged instead of crashing. Let's walk through an actual run of our program. We enter three integers, 10, 20, and 15. Because insert node always inserts at the front, entering them in that order, produces the list 15, 20, then 10. Then we run two searches. Searching for 20 finds it at position 2, and searching for 99 correctly reports not found, demonstrating both branches of find node. Finally, we perform 4 deletions. We delete 15, then 10, then 20, walking through head deletion and tail deletion. And then we try deleting 5 from an already empty list, which correctly reports not found instead of crashing. That covers the full range of behavior for task 1. Thank you. Now with that, I'll hand it over to Soraya, who will walk you through.
Hello ma'am, my name is Akhtar Suraya and my student ID is CST 2509085. Now I will represent task 2, which is implementation of a stack using a singly linked list in C. In this part, I will explain the stack concept, the top pointer, the 4 main functions, the underflow handling, and the menu drive and follow. Finally, the sample output. So let's us begin. First, a stack is a linear structure that follows the last in first out principle, also known as LIFO. Basically, the last value added to the stack will be the first value removed. So a simple real life example is a stack of plates. We place a new plate on the top and we also remove the new plate from the first. In our program, we use a singly linked list instead of an array because the advantage is that an array normally has a fixed capacity, but linked list stack can grow and shrink dynamically according to the available memory. Here, the pointer called the top represents the first node of the linked list. In simple word, top always points to the most recently added value. For example, in this diagram, 30 is the top value followed by 20 and then 10. So since both adding and withdrawing happen at the top, this operation take constant time or big O of A1. So now I will explain the add function. The add function performs the push operation, which means adding a new value at the top of the stack. First, the function creates a new node by using malloc. Then it checks whether the memory allocation was successful. After that, the user value is stored in the data field of the new node. The new node next pointer is connected to the current top, and finally top is updated to point to the new node. For example, suppose the stack currently contains 30, 20, 10. So if I add 40, the new node containing 40 points to 30 and 40 becomes a new top. So the stack becomes 40, 30, then 20, then 10. So the main point is that every new value is inserted at the beginning of the linked list. So next we have the withdraw function. And now what the task of the withdraw functions? This function perform the pop operation, which removes the current top value. Before removing anything, the function check whether the stack is empty or not. If the stack is not empty, it stores the current top node in a temporary pointer and also save its value. Finally, the old top node is released by using the free functions. So for example, if the stack contains 30, 20, 10, withdrawing ons removes 30. After that, 20 becomes a new top. We use free because the removed node is no longer needed. This helps prevent memory leakage. So now let's look at the display function. This function shows all the values currently stored in the stack. If it starts from the top and uses a temporary pointer to visit each node. So at every node it prints the value, then moves to the next node. So if the stack contains 30, 20, 10, the output display values in that same order from top to bottom. If the stack is empty, the function simply prints that stack is empty. The next function is counting. So the first function counts the total number of nodes in the stack. It begins with a counter equal to 0 and visit every node one by one. So for each visited node, counter increase by 1 because it has to visit all the nodes. So the time complexity counting is big O of n. So now another important condition is underflow. So underflow happens when the user tries to withdraw value from an empty stack where there is no element in the stack. So in this situation, first check whether top is null or not. If it is null, the program display the message like the stack underflow cannot withdraw. So this check prevents the program from accessing a null pointer and crashing. The menu also check the empty condition before printing the removed value, so no misleading output is displayed. So now I will explain the overall program, how our total program worked. So the program uses a do while loop together with a switch case statement. The main continues to appear until the user selects option 4. So option 1 is add, option 2 is withdraw, option 3 is stack count, and option 4 is exit. So the option 1, which is add function, so its work is like the program reads a value, calls the add function, and display the updated stack. Option 2 is withdraw, which is like the program check whether the stack is empty or not. If it contains a value, the top item is removed, otherwise the underflow message is displayed. The stack count, which calls the counting function and then display the current stack. And the exit function, before ending the program, clear stack free all the remaining nodes. The default case handles invalid menu numbers, and the program also check the return value of a scan, so non-numeric input can be handled safely. So now I will explain the sample output. First, I add 10. Since the stack is empty, 10 becomes the top value. Then I add 20. So the 20 becomes a new top and 10 remain below it. After that, I add 30. Now the stack display 30, then 20, then 10. So next I select stack count option. So the program reports that there are 3 items which matches the displayed values. Then I select withdraw. The program removes 30 because it's currently at the top. So now the stack contains only 20 and 10. So this confirms that the last in first out principle, because 30 was the last value added and the first value removed. So if I continue withdrawing, the stack eventually becomes empty. So when I try to withdraw again, the program display the underflow message instead of crashing. Finally, I select option 4 to exit. To conclude our presentation, we successfully implement two important data structures in C, a doubly linked list and a stack using a singly linked list. From task 1, we learned how to insert, search, display, delete nodes by correcting, managing the previous and the next pointers. We also handle important edge cases such as an empty list and singly node list, and also values that are not found. So from task 2, we learned how a stack follows the last in first out principle and how the top pointer is used for adding and withdrawing values efficiently. We also handle stack underflow, invalid input, memory management. So overall, these tasks helped us improve our understanding of pointers, dynamic memory allocations, linked data structure, and defensive programming in C. So thank you for watching our presentation.